All right, so we're going to talk about circles and the relationships of circles and how I can calculate some stuff with circles, knowing those relationships. This covers 10.1 through 10.5 in your lesson plans. All right, so we're going to cover the following topics. All right, so we're going to talk about pi, the relationships of pi and how it plays into the diameter, the circumference, and the radius. I introduced to you the idea of an arc length and sectors, and how to calculate all that stuff, knowing what we know with pi. We're going to talk to you about a new idea of radian measures and what the radian actually is. And then we're going to do some problem solvings using all this stuff, knowing all these relationships. Okay, so let's get right down to it. All right, so we all remember that a radius is the length from here to here, and a diameter is a chord that passes through the center point. That's the diameter, and the radius, you remember this important equation that the radius, or 2 radii equals 1 diameter. Okay, so the relationship of pi. So somewhere along the way, let's see specifically, pi was discovered in 1706 by a guy named William Jones. He did some calculus, and he discovered that the relationship between the diameter of a circle and its circumference, or its parameter, or its circumference, so that relationship, now what do we do? Circumference and the diameter. So how do we express relationships or ratios in geometry? Well, that's with a fraction, right? So the ratio, or the fraction of the circumference, which is the bigger number, because it's obviously longer, the circumference to the diameter of a circle will always be this ratio of 3.141592654, and then goes on for a very, very, very long time. But they gave that ratio. So like if you divide it, if you could figure out like the length of the circumference, like you measured it with a string, or you rolled it, like you have like this thing, and like you measured how long it rolled, right, from this point to this point along a ruler. You figured out that circumference, and then you measured the diameter, and you divided the circumference by the diameter. It would always equal that number, and that number is represented by the Greek letter pi. Okay, spelled P-I. P-I. Okay, so that pi shows up in all sorts of equations all the time whenever we're dealing with circles or arcs or part of circles, right? And we square it a lot, and all that stuff, right? So, and we can in our equations, we can replace diameter with a radius and say like, hey, our circumference divided by our radius times 2r equals pi. That's mathematically equivalent because we just did a good old swaparoo or a substitution. And we can rearrange this thing and just multiply both sides of the equation by 2r, right? So that would be like, okay, 2r across the 2, and then it'd be 2r on this side. So you get the good famous equation that the circumference of equation of this equals 2 pi r, right? So 2 times the radius times pi equals the circumference of the circle. Okay, so that is something that is important to remember. Okay, and then remember the diameter. We could go into the derivation of the area of a circle, but I'm not going to get into it too much now. But the area of that circle equals pi r squared. Now you cannot put in diameter here. It's squared because squaring the diameter is not the same as squaring 2 times the radius. It's not mathematically equivalent. Okay, so don't fall into that trap. All right, so how can we use this to our advantage, right? So that is the relationship of diameter and pi and radius, okay? So now what is an arc length? So what is an arc length? Well, in order to know that, you have to know something about a central angle, okay? So we know that the center of a circle is annotated by usually the letter C or whatever we want to name that circle. We're going to name it C here, right? So a central angle is named by the angle on. We're going to name 2 points or more on the circumference of this circle. We're going to name. We'll call this one A, and then we'll call this one like B. Okay. So let's go ahead and connect a couple radii to A and C, and then B and C. Right, these are radii, right, because they're just from the center to the circumference. So those are radii, and then let's say that we identify this angle. Let's see. Now we could actually even say that's. Let's say this one is a CB. We'll call this one D. We'll call that one D, and we'll call this one E. Right, we have multiple different central angles. Okay, cool. So now we can say we have multiple arcs. So let's go ahead and name some of these arcs here, and we'll even color code them. I like color coding. Okay, so we'll have a blue arc. We have a blue one, and we'll say that this angle here. I want this one. So this angle here. Yeah, let's take a look here. Let's get something reasonably close. So this angle here is like, I don't know, like 50-ish. It's like 52-ish degrees. 52 degrees. Okay? And so this arc, we say the arcmeter is 52 degrees. So this measure of this arc, EA, this is the minor arc. Okay, so let's talk about naming arcs real quick. All right, so there's a difference between major arcs and minor arcs. Okay, if I wanted to name this arc, there's 2 ways. The EA bounds 2 arcs. Okay, there's the major arc, which is 52 degrees, the minor arc, which is 52 degrees, and then there's a major arc, which is this one, and we know that there's the angle, the number of angles in a circle is 360. So if we know this one is 52, this one must be the rest, right? So 360 minus 52, this must be 308, 308, right? So this green for this one here, so we'll say the measure of this would be, so how do we differentiate between the minor arc and the major arc? Well, we'll say that the measure, I'll also write it in here, the measure of arc E, we can just pick out any other one of these. Or you could call it measure of arc MCA, right? Or MDA, or MBA, or MAE, right? Or not how it would work, MDA, right? Well, I'm going to call it, if you didn't have any of these, it would be MCA, right? So I'm just going to call it MDA because it goes through D. MDA. It has 3 letters, okay? And it equals 308. Okay? So that is this large one, M. It starts at E, it goes through D, and today you only need 3. You don't need to go all out and go D and B. You only need 3. You could call it D, E, EBA if you wanted it to, but you don't have to, okay? You just only need 3. Differentiate the minor arc from the major arc by using 2 letters for the minor arc, and it's going to be the smaller of the 2 angles. So here the measure of EA equals 52. 52, right? So the arc measure equals the angle measure, or the central angle, right? In terms of the angle. Now, if you were given a length of the circumference here, you could figure out, this is just a simple ratio, right? So, say for instance, with our example, okay, we were given, I don't know, we'll say that the radius, this radii, or all radii here, is, I don't know, let's say 8 units. Actually, it's 9. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 9. It's 9 units. Okay. So, what is the actual length of the minor and the major arc length? Okay. Well, it's pretty easy. Okay. So, we set up a ratio, and we use this equation to figure it out. All right, so we just go the measure, use this one here, the measure of EA equals, right, and we just set up some railroad tracks here, okay. We know we're using 2 pi r, so it's going to be 2 times pi times r. All right, but we're not using the entire 360. This is for the entire 360. We're only using 52 of the 360, right? So it's a fraction, 52 of 360, okay? Or you could just do 52, 360, and it would reduce to 13/90ths. You could do that too, right? Or you can just put 52, 360ths in there. Either way, 52 360ths equals 13/90ths of the 360. Either way, the math checks out. So this would be equal to, let's go ahead and put that in here, so you can show the reduction of the fraction. I guess I want you to do that, 13/90ths. Okay, so then we can go ahead and put in our units. So 2 pi times 9 units times 13/90ths. Now, this is how you do the math. Okay, so just do your 9 times 13 times pi times 2. That's everything on top, divided by 90. That's the only thing on the bottom. Equals, what are your units? The only unit you have to deal with is that. So your arc length here is 8.1, we'll go 7 units. All right, so what is the measure? What is the measure of, let's have a little arc length. What is the measure of the measure of EDA is going to be equal to 2 times pi times r, and this is going to be 308. 308 divided by 360 equals 308 divided by 360. This reduces to 77/90. So that's 77 over 90. All right, so we go ahead and put that numbers in. Again, it's 2 times pi times 9 units over 77/90. Okay, so the only unit we have to deal with, so it's 2 is 9 times pi times 9 times 77. Divide that by 90, and it's going to be 48.38 units. All right, so now, ideally, if we add these up, so 48.38 plus 8.17, it equals 56.55. 56.55 units. It's linear, right? So we're just talking about a line, but it's curved, so it's units, right? So ideally, if we do 2 pi r, it should equal about that. There might be some smudging of the numbers because of rounding, but it's no big deal. Okay, so we just do 2 pi r squared. Oh, sorry, 2 pi r, right? So define that it should equal that, right? So we go 2 times pi times r, which was 9. That equals 56.55. Yeah, there we go. And it equals it. And see, it's really easy. You just take, it's just the circumference equation times the fraction of the circumference that the angle is taking up for the opposite arc. Okay, so it's not hard. Okay, so that is part of that. And the area is the same thing. Okay, so the only difference in area is that you would take the 2 away, right? And the 9 would be squared because you're using the area equation instead, right? The concept is exactly the same. Okay? Now, say for instance, we are doing something a little different. We are trying to determine these values, but we're only given some variables. Okay, and we're trying to solve for the variables and then solve for the actual angles. So let's say that we have angle measure AB, right? And we'll say that this is we'll say 6x minus 9. Okay, and then we'll say that this angle, we'll call this angle, this is red, and we'll say that this is red. This arc is red. And we'll say that this arc is 3x plus 3x. I'll do plus.
Have a good break.
You too. Enjoy your break. We'll do 3x plus 20 plus 18. Plus 18. 3x plus 18. 3x plus 18. Plus 18. Yeah, it's 3x plus 18. That's it. That'll work. Okay, and it's like, hey, solve for x. Okay, and it's all right. This is degrees. Degrees. I'm not sure if this is gonna come out at all, right? We'll see. 3. No, this isn't gonna. Well, it's not gonna work out. hold on, I'm gonna pause this for a second and make some numbers at work. Just a minute. All right, so let's say that angle ACB is 9x minus 8, and angle DCB is 2x minus 8. So 9x minus 7 and 2x minus 8. And we need to figure out what the arc lengths are of AD. We need to figure out AD is. All right. Well, how do we figure out, this whole thing? Well, it's as simple as recognizing that arc AE or AD, excuse me, is 180 degrees, right? Because AED is the diameter, right? So if that's 52 degrees, then the sum of these two angles is 180, or is this whole thing is 180. So the sum of this is going to be 180 less 52, right? So we're going to say that ACD, angle ACD equals 180 degrees minus ACE, angle ACE equals 180 minus 52 degrees equals 128, I think. 180, 80 minus 52 is 128. 128 degrees. So this entire arc, the green and the red, is 128. All right, so now we know that these arcs, so arc, where's my green, arc AB, measure of arc AB, plus the measure of arc DB, measure of, how about I didn't mean to write it like that, DB equals 128. 128. All right, so it's just going to be as simple as saying 9x minus 7 plus 2x minus 8 equals 128 degrees. 128 degrees. All right, so we'll solve for x. It's going to be 11x, shift to burgundy, 11x minus 15 is 128, and then it's going to be 11x equals 128 plus 15 is 143. 143 divided by 11. X is going to be 13. X equals 13. All right, so now x is 13. You plug in x, 13 for that. So this angle here is going to be 9 times it minus 17, or minus 7, excuse me, is going to be 110 degrees. So this is 110. Measure of AB equals 110, and that means 110 plus 52, 110 plus 52 minus 180 is, this is going to be 18. Measure of DB is 18 degrees. All right, and then again you'd use this method here to figure out all that stuff. Okay, let's see. All right, so now that's that. So let's see if I can go through all these. So that's finding out the angle measures and all those things. So let's roll on. So that's 10 point. I guess this would be 10 point. yeah, that's 10.2. Yep, 10.3. We didn't really cover pi yet. We'll cover that next lesson. That's 10.4. And I guess we'll cover 10.5 in depth in another video. No, we covered 10.5. Remember that if we have intersecting lines or intersecting chords, or not chords, but diameters, like this one, all your lines of intersection rules apply too, right? So like 52, these are vertical angles, so this is 52 degrees. So these are the same here. This would be 52 degrees, right? These are a linear pair, so 52 and 52. 52 minus 180. 52 minus 180. This would be 128. So this whole thing is 128, right? So everything that's happening in here reflects out here on the circle. So remember your linear pairs, your alternate, your vertical angle pairs, all that stuff is still going on inside here, and it reflects out here on your circumference. So all that stuff is still pertinent in here. So that's effectively what 5 is saying. So yeah, that's pretty much everything that 5 was talking about too. And remember, a radian, this will cover 6, or this will cover the radian parts. A radian, right? A radian is if you take the radius. What last color do I have? I guess I can use black. I'll use black for this. You take a radius, the length of a radius, okay, and you supersede it, or you transpose it over top of a part of the circumference. That part is 1 radian, okay? And if you were to take and you were to measure or calculate that, and you were to take in your circumference equals 2 pi r, and you were to take 360 degrees in one circumference, and you were to substitute radius for radian, because you know that 1 radius is a radian, so it's going to be 2 pi radian, and you were to solve for the degrees in 1 radian, right? It's 2 pi equals 1 radian equals a radian. Then you would figure out, you just go 360 degrees divided by 2 equals divided by pi equals 1 radian is approximately 57.3 radians. So, or degrees, excuse me. So 1 radian equals 57.3 degrees. Okay, so that's how you go from radians to degrees. Or there's also another relationship. All right, if I have 180 degrees and I divide it by 57.3 radians per degree. Okay, 57.3 radians. Or, excuse me, that's wrong. Let me cross that out. I'll write it down here. Okay, so if I do 180 degrees and one radian is 57.3 degrees. The radians cross it, multiply, and you're left with radians. So how many radians are in 180 degrees? Well, let's figure that out. 180 divided by 57.3. That's a very interesting number. That's pi. That's rounding errors there, right? So you can say that in 180 degrees is pi radians, or there are pi radians in 180 degrees, right? So that's another conversion factor you can use. Okay, so that's another way to know angles or to express angles. For every 180 degrees, there is one whole radian. Okay? Or, excuse me, 3.14 or pi radians. So that should make sense. So 90 degrees is a half of a pi radian. So we'll express that by around the unit circle by saying, hey, this is a pi, and they usually keep radians blank, right? But this would be pi over 2, right? This would be 45 degrees would be pi over 4, right? 1 pi, or pi over 4, 2 pi over 4, 3 pi over 4, at 45, 90, and so on and so forth, right? But that's a little bit beyond the scope of that. All right, so that was 31 minutes. That was all 4 lectures. These are important to know, be able to calculate transfer pi and back to radians, but not too much use of radians in chapter 10. A lot of use of degrees. Hope that helps out a lot, and hope you learn. Have a great day.